A useful concept when talking about vibrational spectroscopy is a concept of normal modes. All right, let's try to see if we can understand normal modes. In general, let's look at degrees of freedom. All right, so let's take, for example, the water molecule, H2O. Each atom in the water molecule generally has 3 degrees of freedom. It can go in the X, the Y, or Z direction. This can go in the X, the Y, or the Z direction also independently, and as can this hydrogen. So for these 3 molecules, or for the water molecule and these 3 atoms, we have 3, 6, 9. So the degrees of freedom for this water molecule to move around in space is 9. Or in general, the degrees of freedom with nothing restricted, degrees of freedom will be 3 times n, where n is the number of atoms in the molecule. Now let's consider what happens if we just want to look at the vibration. So in general, this molecule can translate, go up and down, it can rotate, it can also vibrate. If we want to just focus in on the vibration, what we want to do is to fix this molecule in space. So if we fix in space with respect to rotation, with translation, in other words, what we're going to do is to say, all right, molecule, you can rotate and you can vibrate, but you can't translate. And we mean translate, this means motion of the center of mass. So the molecule can rotate, it can vibrate, but what we're saying by fixing it in space with spectrotranslation, the center of mass can't move around. So this implies we have 3 constraints. So no longer do we have a degree of freedom for the X, Y, and Z with respect to translation. So now our degrees of freedom, when we've fixed it in space, is now 3n, our total number, minus 3. Now what we want to do is don't allow rotation. So what we've done is, okay, you can't translate, now you can't rotate, and what will be left will be the degrees of freedom for vibration. Now for rotation, that also has in general 3 degrees of freedom, and so if we're going to say you can't rotate, we have to fix 3 degrees of freedom, like if we're doing spherical coordinates r, theta, and phi. But in general, we'll have 3 constraints. If we don't allow rotation, so we're going to fix the rotation, and now all the molecule can do is vibrate. So now our degrees of freedom is 3n minus 6, 3 for the translation and 3 for the rotation. But let's look at this a little more carefully here for linear molecules. Suppose we have a linear molecule, for example, we have HCl, linear molecule. If we look at this, let's draw the axes on here. So this bond axis here, the axis of the bond, say is the X direction, this is the Y, and this is a Z. If we rotate around the X axis, we find that, well, nothing happens. You're not actually rotating the molecule, you're just rotating around here and the molecule stays fixed in space. So really for a linear molecule, you only have 2 axes, 2 rotational axes. See, if you rotate around the y-axis, this can rotate in space. Around the z-axis, it can rotate in space. But not around the x-axis, nothing happens. So this implies that you only have you only need to specify 2 constraints for a linear molecule. So now this implies that the total number of degrees of freedom after the translation and after the rotation for a linear molecule is 3n minus 5 for linear. All right, so that's the number of degrees of freedom that we're left with in order to specify. Now those degrees of freedom are represented by normal modes of vibration. So there'll be 3n minus 6 or 3n minus 5 for linear molecules. Okay, so what do we mean by that? Well, again, let's take the water molecule as our example. All right, so think about all sorts of vibrations. Now remember, this is not going to translate, it's not going to rotate, so we can just have it here fixed, and we're now going to look at the vibrations, and the center of mass is not going to change. So let's say move this one up and move that one over there. So now we have this kind of vibration. So that shortens, and this, say, shortens, or no, let's make this longer, and it moved over there. So H. There's one kind of vibration, or we can vibrate it again. And we do this in such a way that the center of mass doesn't change. Let's do, no, just for fun, let's do this one. Let's vibrate that one there and that one there. So now we have something like this. And let's vibrate it again. So we have all sorts of vibrations here. I don't know. Here's a sort of extreme vibration, H. And there's a short bond there and so on. So there's a whole bunch of different kinds of vibration. The key point about normal modes is that all those vibrations can be expressed as a linear combination of the normal modes of vibration. That's why you talk about normal modes. The number of normal modes, because we're going to describe the vibration, has to equal the number of degrees of freedom. So the number of normal modes is equal to 3n minus 6 or 3n minus 5 for linear molecules. Let's look at water. Water has n. Remember, n is the number of atoms. Water has 3 atoms. It's not linear, so the number of degrees of freedom, once we dial out the translation and rotational degrees of freedom, what's left for vibration? 3 times 3 minus 6, or 3 normal modes of vibration for water. And again, as we said, because we're dialing out the translation and rotation, the center of mass doesn't change during a normal mode vibration. The molecule, essentially, if you move one atom, you have to move another atom so that the center of mass doesn't change. Some vibrational modes are degenerate. Here we're using the word degenerate in the same sense we used for wave functions, namely that some vibrational modes, the energy of the molecule doesn't change. And here's an interesting point. And why do we study symmetry to begin with? Well, here's an application of symmetry. Each vibrational normal mode, it should be normal mode, is associated with an irreducible representation of the molecule. So remember, a molecule belongs to a certain point group. The point group has different representations of its symmetry. Each normal mode has associated with it an irreducible representation. So that's where you get the idea, like the irreducible representations represented a basis set, an orthonormal basis set, by which you can represent any kind of symmetry. Well, the same way, the vibrational modes form if you extend the term orthonormal, they form an orthonormal basis set by which you can describe any vibration of the molecule. And then when we I should be checking these off as we do these. Okay, we've done all those. Now, maximum number of transitions is equal to the number of normal modes. That's where we go into spectroscopy. So we have a molecule. It can vibrate. The vibration can be described in terms of 3n minus 5 or 3n minus 6 normal modes. And that is the maximum number of transitions that you could ever see in a vibrational spectroscopy. For example, water has 3 normal modes. So the maximum number of vibrational energy level transitions you could ever observe in an IR spectrum is, for water, 3. Now that's the maximum. Of course, there may be some that are not visible in IR or some degenerate or so on, but we can have up to a maximum of 3. If you take the spectrum of a water molecule and you find more than 3, oh, well, you probably have a contamination. Now, here's an animation of some normal modes. This is not water, by the way. This is something else. So this is the different kinds of, this is a carbon, hydrogen, hydrogen, and these are some normal modes. So these, here the C is for CH2 group. Here the hydrogen coming out towards you and away, out and away. Here they're sort of wagging this way. Here's another one, another one, another one. So any vibration of a CH2 group can be described in terms of a linear combination of these. Now let's see what we can figure out. Here's a bunch of vibrations of water. Let's see if we can figure out what the normal modes of water are. Takes some practice, but eventually you get used to it. So here is the water molecule which is in its equilibrium state, meaning there's bond is neither compressed nor expanded. Let's move this one out here and this one out here along the direction of the bond here. So that's going out and out. Now note that this, if you just have these two moving, the center of mass now will change. The center of mass is about right here. As these move out, the center of mass goes down this way. So what you want for a normal mode is for the center of mass not to move. So here we have to compensate for those hydrogen movements by movement of the oxygen molecule, but on the opposite direction. But the oxygen molecule doesn't have to move as much as these hydrogens to maintain the center of mass, because the center of mass is weighted. All right, so that's one normal mode. Let's look at another normal mode. Let's do, and here this is at the equilibrium state. Let's move this out, and let's move this in. So now we have this stretching and this compressing. That's another normal mode. And the third normal mode of water, here's our equilibrium structure. Let's move this in this way and that in that way. So now we have that sort of motion. All right, and of course, once it compresses, then it'll expand. So this is really a two-way. But the initial direction, I guess I should write the initial direction, that expands or that stretches and this compresses. And here they're just wagging this way. All right, so there's three normal modes of water. Generally, you have computer programs. Given a structure of a molecule, the computer program then can figure out what the normal modes are. And in lecture, I'll demonstrate a computer program that will do that. In fact, that's the computational chemistry program. So that's an introduction to normal modes. We'll talk a little bit more about this later on when you talk more about vibrational spectroscopy.